Now we shall take up the important topic of dislocations. We will talk about edge dislocations, screw dislocations, mixed dislocations, and the importance of dislocations in crystals, especially the way they affect the material behavior. There is a lot of very good literature on dislocations. A nice interesting introductory text would be by Hull and Bacon, which forms a nice interesting reading. For people who are interested in more advanced concepts and especially a comprehensive treatment of dislocations, the theory of dislocations by Hirth and Loth is a very good text. There are some nice websites also, like the one which is in University of Kiel, which also gives comprehensive information about dislocations. The first and foremost important thing I would like to say about dislocations, and we already said that dislocations are line defects, that means they can be considered as one dimensional defects, is the fact that their role goes far beyond plasticity by slip. This of course we have not defined what is plasticity by slip, but it is as you know associated with plastic deformation, but the role of dislocation goes far beyond that. In fact, they play a very important role in deformation processes like creep, fatigue and fracture. So, whenever people focus on the role of dislocations in plasticity, we should remember that that is just one important role, but there are many other important roles of dislocations in very diverse kind of phenomena, and in the next slide we will take up a nice graphic which explains this overview. Apart from these deformation processes like plastic deformations like normal plastic deformation, creep or fatigue or fracture, they can play actually a constructive role in crystal growth, and typically screw dislocations play a very important role in crystal growth, and therefore, we will see that often dislocation is talked about as a defect, but even though in spite of being a defect, they can actually play a very important and very surprisingly constructive role in the very growth of crystals. So, that is a very important role that dislocations can play, and in this context we will say these are the screw dislocations which play that role. They can provide short circuit paths for diffusion, and typically the diffusivity which occurs at the core of dislocations, that is through the dislocation region, which is called the pipe diffusion, as a diffusivity which is much higher, orders of magnitude higher than the normal lattice diffusion. And we will of course try to understand that why this is so, and this will become obvious by the time we understand the structure of a dislocation. And in this context, I would definitely like to say that the importance of dislocations in material behavior cannot be overstated. The more we try to understand dislocations, the better our understanding of material behavior will be, especially the mechanical behavior of materials. Of course, their role is not just related to mechanical behavior. For instance, in electronic equipment and devices, if there are dislocations in the semiconductor for instance, then the material behavior could be adversely affected, and therefore we need to understand the presence of dislocations, how many dislocations can be tolerated for instance in a semiconductor device and so forth. And in this context, definitely that we need to thoroughly understand the structure and behavior of dislocations if we want to comprehend the material behavior, starting from of course the microscopic scale. Just to reiterate the important things in this slide, that dislocations are very important and we need to understand them thoroughly. To understanding the role of dislocation in material behavior, of course this is similar to the path we undertook for understanding any kind of defect, but here specifically we are dealing with dislocations. So, the first thing we will do of course is to consider an isolated dislocation in an infinite crystal. So, this is some sort of an ideal description of a dislocation, and we really know that for instance there are no infinite materials, and often we will always deal with finite sized crystals, and not only just a single crystal, but often this could be even a polycrystal. But we will start with a description of a dislocation in an infinite medium, and we will try to understand things like for instance stress fields, strain fields, the energy of a dislocation, etc. Then we will proceed or we should proceed to taking into account finite size crystal effects, like what do free surfaces do to for instance the stress field of a dislocation, or what is the effect of a grain boundary on the motion of dislocations. So, these kind of questions we should ask. In this introductory course of course we will not take up all aspects of dislocation, we will just take up perhaps a descriptive sample, and then the remaining perhaps would be left to a more advanced course on plasticity or some of those other kind of courses wherein you will deal with more advanced concepts. Then after considering finite crystal effects, we need to consider interaction of dislocations, and we will of course consider in this course a few examples of interactions between dislocations, and this interaction is not only between dislocations, it is between dislocations and other kind of defects in the material. These other defects could be vacancies, they could be grain boundaries, there could be twins or any other kind of defect. So, we need to understand the interaction of dislocations with other defects in the material. this is an important topic. And then finally, the goal is to understand collective behavior of dislocations, and this is a very challenging task of material science, wherein you try to understand that how not a single dislocation, but thousands of them or even millions of them are moving together, interacting with each other, interacting with free surfaces, interacting with precipitates, and finally all this evolution is taking place in time and under the action of external constraints. So, external constraints could be displacement boundary conditions, they could be stresses imposed or forces imposed on the body. Of course, you could visualize the simplest case being an uniaxial tension test. So, there are these external constraints which are perhaps driving these dislocations, and these dislocations are evolving in time via their interactions with each other and with other defects in the material. So, these long range interactions and collective behavior is of course a very challenging problem in material science, but that is the real goal of this whole task of starting from a single dislocation. Many of these aspects, though they are written separately in a very sequential form, these can also be considered parallelly in many of the approaches. Actually, that is what is precisely done. You do not start with a single dislocation and try to evolve the entire behavior, but you start the whole description process starts with a more collective or an average kind of a description of the entire deformation that a dislocation perhaps would give. Not only we need to consider static dislocations, but we also need to take into account dynamic effects, and that is a very important thing. For instance, like a moving dislocation has an altered stress field with respect to a static dislocation, and suppose the velocity of the dislocation increases, it starts to approach the speed of sound in the material, which is the shear wave velocity in the material, then there are serious dynamic effects which cannot be ignored. And these dynamic effects are also evolving in time obviously, and this makes the problem very complicated. And this sequential thought process we have evolved now is more of a understanding or a didactic thought process, and in reality this step by step method may not be followed, and a practical there may be techniques which take up the collective behavior directly. So, there are techniques in dislocation plasticity wherein they actually take up a large scale descriptive or an average parameter description of this material behavior directly without going through a step by step process, which we have illustrated here for a better understanding of the kind of concepts we will be going through in this elementary course. Yeah.
Sir, the stress field and strain field, are these interdependent to each other, or are these two separate properties?
Okay, a good question. In this case, obviously they are interdependent with each other, because the stress field is related to the strain field via the material properties. Okay, so that is very clear in this case. But as a macroscopic case, as you know that for instance you could have stresses without strains and strains without stresses. So, that is the macroscopic. Like suppose I take a rod and put it between two rigid walls and then heat the material, then the rod is not allowed to expand, but stresses do develop in the material, and but this is now stresses without strains. The other extreme example would be the same rod which I just allow to heat. In that case, it just freely expands in the medium. In that case, there is strain, but there are no stresses, because now all the stress is relieved by the expansion of the rod. So, that is the macroscopic description. In this case, stress fields and strain fields are intimately associated with each other. Okay. Now, I was talking about the role of dislocations in materials, and I had warned that though plasticity by slip, which is the one which is first in this slide, is a very important aspect of the behavior of dislocations or the role of dislocations, but their role goes far beyond, and all these aspects put together is what we need to keep in mind when we are trying to understand dislocations. They play a very important role in various deformation processes. Like I had mentioned, they play a role in normal plastic deformation, in fracture, in fatigue, in creep. For instance, when I am talking about fracture, we will see that if I have a sharp crack in a material, like the one I can draw in a board, and this kind of sharp cracks typically are in brittle material. So, I have a material like this, and now I have a sharp crack. So, this is a brittle material. Suppose I had a ductile material, then what would happen? This sharp crack would actually blunt, and this blunting process is aided by the presence of the plasticity by dislocation. So, this because of this blunting now, there is, for instance, if I had a sharp crack, then I would have a singularity in the stress field. That means the stress field would blow up at the crack tip. But in this case, because of the blunting of the crack, the stress field will not blow up, and actually you can draw a stress field which actually goes up and comes down. That means now that there is a very important role of dislocations in causing which is very intimate relationship with fracture. Okay. Suppose if I had a specimen like this, then this would fail by brittle fracture, and in this case, because the crack tip has been blunted, there will actually be ductility in the material. They also play a very important role, for instance, in nucleation of fatigue cracks, and you know, fatigue loading is when you have a oscillating sort of a stress field. That means it changes sign, or it could actually go through an up and down, and in that case these dislocations could move and come to the surface, cause surface steps, which actually could act like surface intrusions, surface extrusions, which would actually act like cracks. So in other words, the very process of dislocation motion, which is of course happening by slip at the microscopic level, can give rise to a macroscopic kind of a crack, or a slightly larger scale microscopic kind of a crack, which is related to fatigue cracks. Then also play a very important role in creep and related phenomena. So dislocations have obviously a very important role in deformation process, but we should also know that, for instance, they also play a very important role in kinetic process, like for instance in diffusion, and we already talked about these two aspects, the diffusion and the crystal growth. So they can actually, as we saw, perform a constructive role, okay, like in crystal growth. As we said, defects can be classified as structural and non-structural defects or statistical defects. The structural role of dislocation is also very important. For instance, they can play a structural role in incoherent twins as a low angle grain boundary, a low angle, and there are two kinds of low angle grain boundaries, as we shall see in the next chapter, which will be on surface defects. Like there will be the tilt boundary and the twist boundary, and in both these cases they are dislocations which are responsible for that tilt or the twist. They play a very important role in semi-coherent interfaces, and as we shall see, for instance, when you have a disk of vacancies on a slip plane or a certain crystallographic plane, then they can be thought of as an edge dislocation. So we can see that not only dislocations have a very important role in deformation processes, like in the left of the slide, they have very important processes in various kinetic roles, and they have a very important role in structure of material, the structural role. And some of these examples of the structural role we will actually take up during these set of lectures. Yeah, there is a question.
Sir, can't edge dislocations also help in crystal growth?
Good question. We will perhaps come to it a little later, this question of what role they play in crystal growth. Okay. Yes, they can actually, because this, when the edge dislocation leaves the surface of the crystal, for instance, then they can provide a high energy site, perhaps, which would be good for an atom to actually adhere to. But that role is much limited as compared to the role of screw dislocations and crystal growth, wherein they clearly provide a very preferred site for the atom to attach to. Okay, so in the case of screw dislocation, very clear, but yes, edge dislocation also could provide a high energy area where heterogeneous nucleation could actually take place of the atom. That means the nucleation of the surface step could start over there. But of course, we should note that when though we are defining certain kind of dislocations as structural dislocations, these dislocations also can play a role in deformation and kinetic process. That should not be forgotten. This visualization or this classification is for better understanding of these kind of defects in their various roles. But even suppose you had a low angle grain boundary wherein you had an array of dislocations, some of these dislocations also could leave the grain boundary and play a role in plasticity, or this grain boundary could pick up more dislocations and actually increase the tilt angle. So both these cases are possible. In other words, their role would extend beyond just being a mere structural unit. So this overview slide would have told you the importance of dislocations in diverse kind of material behavior and material structure. So that's what is the key, perhaps the most important slide in this whole course, and this overview slide has to be kept in the mind when you are dealing with dislocations. Now we had mentioned that dislocations play a very important role in plasticity. That means, suppose I take a rod of copper and bend it, so it bends easily, and if I take a rod of steel and bend it, I will find it is a little more difficult to bend a rod of steel. So of course the questions I can ask is, first of all, is that why this is so, but the kind of deformation, that means that irreversible deformation, that means when I removed my stresses, the deformation, the bending still remains, and that is what I call plastic deformation. And the primary agent responsible for most of the cases for plastic deformation is dislocation motion, or motion of a large number of dislocation, and this is called plasticity by slip. But we should not forget that even though this might be the common mechanism in our many of the cases we often consider, that there are other mechanisms of plastic deformation which could play for instance a predominant role under certain circumstances, and these include twinning, phase transformations, and there are many creep mechanisms which also can lead to permanent deformation, which we can call plastic deformation. And this is what we may call the plastic deformation material of crystalline materials. You could have a whole set of plastic deformation mechanisms for partially crystalline materials or even amorphous materials. For instance, I am talking about BCC materials at very low temperatures, then plasticity by slip could be very limited, and in those cases twinning plays a very important role in giving rise to whatever deformation that I observe. So, twinning can play a very important role in plasticity. Phase transformation, for instance, again as you know, can even play a very important role in actually strengthening materials, inhibiting the role of cracks in materials, but they also can be responsible for plastic deformation. You know, suppose I had a single crystal which goes from a cubic phase to a tetragonal phase, then this would be obviously be accompanied by a certain shape change, and this would be a permanent irreversible plastic deformation, and this could even be caused by temperature, as you know. So, we need to keep this other point in view, because often we will be talking about plastic deformation as if it is synonymous with slip. That means the role of dislocation would be perhaps the most important one we will consider often, but we should not forget that there are other mechanisms of plastic deformation, and these other mechanisms could actually play a very important role in certain other circumstances. And these other mechanisms, for just for a revision, are twinning, phase transformations and creep mechanisms, and these creep mechanisms could involve grain boundary sliding, vacancy diffusion and dislocation climb. And so, you can see that even within the creep mechanism there is a role for dislocations with regard to the way the creep takes place. So, with these two important overview slides, first the role of dislocations and the various plastic deformation mechanisms, we are in a position to actually take up the most important question perhaps, which or the most important mystery that actually dislocations led to solve. So, let us consider, to understand this role of dislocations, then let us consider plastic deformation by shear. So, as I was defining, plastic deformation means permanent deformation which remains in the material when external stresses or external forces have been removed. So, in the absence of external forces, whatever strain remains in the material, that is the plastic strain. So, typically, for instance, suppose I had a rod of metal, I pull it, then if I release the external load, then what would happen, that some of it would recover back, which is called the elastic deformation, but the remaining of the rod would remain in the extended state, which is because of the plastic deformation. Under most circumstances, under normal circumstances, as I pointed out, it is the role of dislocations which causes this kind of a plastic deformation. But going back historically, say putting us back about 100 years back or 80 years back, it's the simplest way a plastic deformation can be conceived is actually, suppose you had a row of atoms as shown here and you apply some shear stress. So, what would happen is that this row of atoms would slide into a new position which is shown on the right hand side. In other words, this atom would actually climb and get into this new position. So, this is an equilibrium position of this atom A, for instance, and this can actually climb over the other atom and get into equilibrium position which is B, which is of course, as far as the macroscopic picture goes, are identical configurations of the crystal. But the end, suppose now I consider my configuration as A, X, Y, Z, then this new position would be A, X, Y, Z. So, you can see that this has been sheared, the shape has changed to this new kind of a shape as compared to this old shape which was these two atomic planes. So, if you have many rows of atoms, then this would go from this shape to this shape. So, this can be thought of as plastic deformation, or more if you want to be more accurate or more descriptive, this is actually the first step of what you might call a gross macroscopic shape change or plastic deformation. So, if I want to consider a plastic deformation wherein I am just shearing one row of atoms over another row of atoms leading to a stable configuration as in the right hand side. So, this is my stable configuration on the right hand side, wherein atoms are not going to further deform. But to go from configuration on the left hand side to the right hand side, I need to apply shear stresses, and we shall see this theme that shear stresses play a very important role at the macroscopic scale in causing plastic deformation. Now, if the spacing between the atoms, the interplanar distance is A, and now the interatomic spacing along the direction is B, then you can see that both of them remain same after the deformation has taken place. Now, I can think of a force displacement curve or a shear stress displacement curve and displacement of course in this case being x, then I can think of a shear stress displacement curve which has some sort of an sinusoidal kind of a shape. More realistic calculations have shown actually it is not truly sinusoidal, but it has got a more complicated shape, but for now we will assume a sinusoidal kind of a shape to illustrate a very important point. So, that is my blue curve which you can see here, right, the blue curve which is the curve which goes in a sinusoidal fashion. The important point to be noted in this curve is that initially you need to apply increasing amount of shear stress, and afterwards actually the whole process takes place downhill, and after some time, as you know, it takes a negative value. In other words, the system actually tends to fall into an equilibrium position after it has reaches the maximum. So, the important quantity in this entire deformation process is the maximum shear stress tau m, which I need to apply so that this configuration on the left hand side goes to the configuration on the right hand side. So, if I apply a tau m shear stress, then I am guaranteed that the configuration on the left hand side goes to a configuration on the right hand side. So, assuming a sinusoidal kind of a relationship in the stress displacement, and of course, I am talking about shear stress displacement relationship, then as to a first approximation, I can write the stress displacement curve as a sinusoidal function. That means tau, which is the shear stress I need to apply, is a function of tau m sine of 2 pi x by b, where b, as I pointed out, is the distance between the atoms along the direction of shear, and x is the displacement which I am talking about. So, I can write tau as tau m sine 2 pi x by b. At small values of displacement, I can assume that Hooke's law actually applies, and I can write tau as g gamma, gamma being the shear strain. And since gamma is again small, I can write it as x by a, and x, as you know, is the displacement and a is the interplanar spacing, right. Therefore, I can write constructing a triangle in this direction, for instance now. So, this is my a direction, I can construct a triangle, and this is my shear strain gamma, and this is my x, and this is my a. So, I can actually write it as g gamma, which is g into x by a. For small values of x by b, which is what again I am talking about small shear strains, that means that this relation on the top can be reduced to the relation at the bottom, where tau is equal to tau m 2 pi x by b. So, sin theta has been approximated to theta. Putting these two relations together, one is coming of course from Hooke's law, and the other coming from the sinusoidal kind of behavior which we have assumed for the stress displacement relationship, we can actually write the g x by a equal to tau m 2 pi x by b. That is what I have done here. G x by a is equal to tau m 2 pi x by b. So, we can obviously cancel out the x's on both these sides, and we can write tau m is equal to g by 2 pi into b by a. Now, b is obviously of the order of a, and therefore, since we are in this whole calculation, we are worried about an order of magnitude calculation, we are not interested in the details of the actual numerical values. So, I can actually replace, I can cancel out, or we can make this approximately is tau m, the maximum stress required for causing plastic deformation is g by 2 pi. Reminding ourselves again, tau m is the maximum stress I require. I do not have to worry about the other part of the curve, because after that it will spontaneously go downhill in stress. Therefore, tau m is equal to g by 2 pi, or I can approximate it even further and say that tau m is of the order of g, where g is the shear modulus of the crystal. So, by considering a shearing of two planes of atoms, which is giving me plastic deformation, and by assuming a sort of a sinusoidal stress displacement relationship, I have seen that the maximum stress required to cause this plastic deformation is of the order of g. The shear modulus of metals is typically of the order between 20 to 150 gigapascals, and the important thing I need to note is the word gigapascals here. So, it is of the order of 10 power 9 pascals. So, 20 to 50 10 into 10 power 9 pascals. Now, given the fact that tau m is g by 2 pi, the theoretical shear stress will be in the range of 3 to 30 gigapascal. Why do I call this the theoretical shear stress? Because the keyword here is theoretical shear stress, because I have theoretically calculated the shear stress required to cause plastic deformation by shear. And now, this is in a perfect crystal in the absence of any kind of defect. That is obvious, because I know I am not introducing any kind of defect in the material, I am actually shearing a crystal purely by applying shear stresses. So, the theoretical shear stress now to cause this kind of a plastic deformation would be of the order of 3 to 30 gigapascals. So, on rough order I could assume it is about 10 gigapascals if you want, but the key thing to note, it is of the order of gigapascals. So, that is the key thing. Now, when I do a measurement of actual shear stress of materials, and lo and behold that the actual shear stress required to cause plastic deformation, suppose I take a rod of aluminum or take a rod of copper or take a rod of iron and try to cause plastic deformation, then the shear stress comes out of the order of megapascals. So, clearly crystals are weaker at least by 2 to 3 orders of magnitude as compared to the theoretical shear stress or the theoretical shear strength predicted. So, often you will notice that the word strength and stress are used synonymously. Whenever we say strength of a material, we mean it is in the stress units, Newton per meter square. So, the theoretical shear strength or the theoretical shear stress is off by at least 2 to 3 orders of magnitude as compared to the practical value, that means the experimentally measured value. For a long time this was a big mystery, long time meaning up till the early 1930s, that why were crystals so weak? Why is it that when I try to make a theoretical calculation, I get this shear stress of the order of gigapascals, but when I actually make a measurement of the shear stress required to cause plastic deformation, I find it is of the order of megapascals. Clearly crystals are very weak. So, this mystery was finally solved in the 1930s, as we shall see, by Taylor, Orawan and Pogliani, and of course independently they had solved this mystery. And the reason for behind the weakening of this severe weakening of crystals is the presence of the defects, which we call dislocations. So, the first and foremost most important role we need to understand of dislocations in materials is the severe weakening of the crystal in the presence of dislocations, and this is not just a mere factor of 2 weakening, it is a weakening by a few orders of magnitude. So, that is what is important, and we note that the shear stress theoretical is more than 100 times the shear stress experimental, and dislocations are severely weakening the crystal. That means that if I made a crystal without any dislocations, I would be able to retrieve very high strengths in the crystal. Of course, if I try to apply very stress of the order of gigapascals, what would actually happen is that these stresses would actually nucleate dislocations in the material, leading finally to the weakening of the crystal. But even then the stresses required to nucleate dislocations are much higher than the stresses required to propagate them, which is the propagation of dislocation is what causing plastic deformation. Therefore, since the stresses for nucleation are much higher than the stress required to move dislocations, which is giving me my plastic deformation, crystals without any dislocations are much stronger than crystals with dislocations. And actually crystals without dislocations have been formed, and these are called whiskers, very thin filaments which have absolutely no dislocations, and therefore they are actually very strong, and you could actually go to very close to the theoretical shear strength of materials. So, the first and foremost important lesson which you have learnt is that dislocations severely weaken the crystal. Of course, is this a bad thing, is it a good thing, is a different question altogether, and a good or a bad depends on the context here. As we shall see, suppose I am wanting to form a component. I want to take a metal which is in the form of sheet and form it into form a cup. So, I am using a metal forming operation. For this kind of a metal forming operation, say schematically, let me draw this. Suppose I had a sheet here, sheet of metal, and I wanted to form it in the form of a cup. So, I would want to form it. So, this could be a of course slightly larger cup, or of course I could draw more schematic cup like this. So, I need a die, and of course I will punch this to form this cup, and in this case I do not want the crystal to be too strong, because I want to deform it at lower stresses. If the stresses required to cause a deformation is very large, then what would happen is that of course there will be other competing mechanisms like fracture. So, the material will fracture actually before it actually plastically deforms. Of course, even if there is no fracture, I need to, if the stress required is very high to cause this deformation, then I need to buy presses which are much higher in capacity, which is going to cost me a lot of money, and the tools will wear out much faster, and therefore, in this context actually the weakening of the crystal is actually good. So, leaving aside the issue that actually is weakening of the crystal good or bad, the fact we need to note is that dislocations severely weaken the crystal, and as we noted, they are the primary agent responsible for plastic deformation. So, to proceed to the next level, we have seen that dislocation can play a diverse kind of roles in material structure and its behavior. and the structural role of course we will take up a little more later on. And the most important of these we have noted is the weakening of the crystals in the presence of dislocations. So, that is an important thing we have noted. We also noted from the previous slide that the path to understanding dislocations in materials involves their interactions with other dislocations and defects present in the material. So, this is an important thing we have noted so far, and the evolution of the whole defect structure with time and with the deformation. So, it is not like the defect structure is constant, dislocations are moving, they are leaving the crystal, there are interaction between dislocations and there are fresh dislocations being created, there are other kind of point defects being created. So, the whole picture is a dynamic picture evolving in time, and obviously this time is the time scale of the deformation. In this whole process we will see that actually the material gets harder. So, there is something known as strain hardening, that means the crystal gets harder and harder as you cause plastic deformation, and this itself is actually a very surprising aspect, though perhaps we will not take it up in this at this point in this course. And this hardening is a very interesting thing, because when you had a single dislocation the crystal became weaker, or a few dislocations the material, the crystal became weaker, and as plastic deformation proceeds, that means you say for instance you have a tensile rod and you are pulling it and you are causing larger and larger plastic deformation, then you would notice that the crystal actually or the material actually gets stronger and stronger, and this effect is pronounced in polycrystalline materials. Now, this hardening of the material is because more and more dislocations are being generated during the deformation. That means the dislocation density is increasing, and we know the units of dislocation density, it is length of a dislocation line in a volume of material. So, as the dislocation density is increasing, the interaction between dislocations becomes more frequent, the interaction of dislocations with point defects, with grain boundaries and other defects become more frequent, and this process leads to actually the strengthening of the crystal. So, a single or a few defects is bad for the crystal, it causes weakening, but we could, when this thing goes further, actually you see that there is a strengthening of the crystal by the presence of many dislocations. So, this a good analogy perhaps, or some sort of a crude analogy for this would be, suppose you had a road and you had a few cars, these cars can actually escape very fast, they can drive very fast on the road, but if you have too many cars then there will be a traffic jam. So, something like that, when there are too many dislocations, they interact with each other, this actually leads to the strengthening of the crystal, and actually this is one of the techniques in fact used for strengthening of a crystal, which is the method of work hardening or work hardening of the material by plastic deformation. So, this hardening effect is coming by the interaction of multiple dislocations, and this is one of the reasons why we want to consider the collective behavior of dislocations and their interactions. So, before we proceed to the next slide, as I had pointed out, there were some many important path breaking ideas which came with the proposal of the dislocation theory. So, but the most surprising thing was that the whole idea of dislocation came with Taylor, Orowan and Poliani in the 1930s, and this of course I am talking about the concept of a crystal dislocation, which came of course considerably after the concept of something known as the continuum dislocation, which came from Vito Volterra in 1905, and we will take up that concept a little later. But the surprising thing is that till 1930s, which is of course or the early 1930s, wherein people understood quite a bit of quantum mechanics, they understood the subatomic realm, they understood the evolution of galaxies, they understood relativity, they could even predict what was how was the beginning of the universe, but they could not understand why a rod of copper could be bent so easily, because we saw that the theoretical calculations tell you that the rod of copper is much weaker in practice as compared to a theoretical calculation, and this was not explained for a long time. So, this is very surprising, but these three scientists came up with the model of the dislocation in 1930, and in 1950s this concept of a dislocation was electron microscopically confirmed. The presence of dislocations were confirmed using an electron microscope. So, some of the path breaking ideas on dislocations came between about 1930 and 1950, and these include the concept of the crystal dislocation, but we will also consider something, the Volterra's dislocation, which is a continuum concept of a dislocation. So, how do I understand in a more common sense way the weakening of a crystal in the presence of dislocations? So, that is the first question I am asking myself. That of course, I know that crystal is being weakened by the presence of dislocations from by comparing the theoretical result with the experimental result, but the common analogy which is given to understand this weakening of the crystal is the one of a pulling of a carpet. So, suppose I have a carpet which is a two-dimensional carpet, and it is assuming a very large carpet covering a large surface area. and I am trying to pull this carpet. So, if I pull it by sliding along the floor, then obviously the friction between the carpet and the floor is going to give me some resistance. So, the effect, if the carpet is pretty large, assuming it is a carpet as thick carpet which is as large as a room or bigger than a room, then the effort required would be pretty large. Now, so the first thing is that I have a carpet and I am trying to pull this carpet onto the right hand side. So, what I am trying to do is pull this carpet on the right hand side, and I would find that the stress required is very large. The alternative is to actually create a small fold, which you can see here, which is shown in the red, and then this small fold or a bump and can be moved across the length of the carpet, and at any point of time you would notice that I am not pulling the entire carpet, I am just moving the bump along the carpet. So, I make a bump in the carpet, and this small bump I slowly move forward, and you will notice that if I try to do this at each point of time, the stress required to move this bump is actually much smaller than to move the entire carpet. So, when I move this bump across the carpet, and finally when the bump leaves the carpet on the right hand side, I get a little extra length, which is because of the fold which was originally created. So, I have a length which is moved to the right. In this process, of course, I am not moving the entire carpet in one step, but has broken down the problem of moving a carpet into small steps of creating bumps and rolling the bumps over to create this small step. Later on we will see that this has a very close analogy with dislocation motion, and this later on this step which has been created would be called a Burger's vector. So, later on we will see this. Now, suppose I have moved the carpet a little distance and this is now B, I can do the process again by make another fold in the my carpet and then move that forward, and slowly I can move the whole carpet forward. But the whole process now takes much less effort from you as compared to a single effort of moving the entire carpet. So, this is the common analogy given between how a dislocation weakens a crystal and how for instance a pulling of a carpet can be done with a less effort in the presence of these bumps which are rolled forward. So, before we actually take up the dislocation in a crystal, which is of course is of the most important what you might call consideration here, we will take up a continuum description of a dislocation. So, this was done, as I pointed out, in 1905 by Vito Volterra, and this is called the continuum concept of a dislocation. In this case, there are no atoms, there is no crystalline order which we are considering, it is just a material which is a simple smooth continuum. But the important thing to note is that his ideas and calculation and many of the things which he had proposed actually which predate their application to crystals, but even today the continuum calculation based on Volterra's ideas are very important for us to understand the stress fields and the behavior of dislocations in crystals. So, some of the behavior of dislocations and often the collective behavior of dislocations is that these stress fields and displacement fields etc., which are related to dislocations are found to be valid within a few atomic spacings, or to be more precise within a few Burger's vectors, and the continuum theory only breaks down very close to the dislocation line. So, even though we know that this the dislocation resides in a crystal and it is a crystallographic defect, but continuum ideas can give us a very important understanding of dislocations, especially their stress fields, their motion and even their collective behavior, and the continuum theory only breaks down very close to the dislocation line, and which is about 5, some people say it is 5, some people it may consider as 1 Burger's vector, but a few atomic spacings from the dislocation line. So, and you will notice that the stress fields which we will be quoting in this chapter are actually derived based on the elastic continuum theories. So, and this is a very strange aspect, as I shall say, because we have used the elasticity theory has been used to calculate the stress fields of the most important agent which is responsible for plastic deformation. So, we are using elasticity theory to calculate the stress fields of a dislocation, which is the agent primarily responsible for plastic deformation. So, this is a very strange but important effect. So, what is the Volterra's picture of a dislocation? In Volterra's picture, you take a hollow cylinder, that means I take a cylinder wherein there is material here, and I try to make a cut in this cylinder which is shown by this grey area. So, this is my grey area wherein I make a cut in the cylinder. So, this is a hollow cylinder in which I make a cut, and after making the cut I make various deformations to the cylinder, and we will only consider the important ones from this perspective of dislocations. In fact, you can actually produce edge dislocations, screw dislocations and disclinations based on the idea of Volterra. So, how can edge dislocation be made? You can actually push in one part of the cylinder with respect to another part of the cylinder. So, you can push in this part. So, how do you do that? Since now the cut has been made, so you can push in this part, the upper part and pull out this part, and you will make a small step, which is the step here. And this is one way of creating some sort of an edge dislocation. Another way of creating an edge dislocation is actually pull these two apart. So, you will get an edge dislocation. So, in the two dimensional picture you can see that in this case you are actually pulling apart and creating a small displacement B between the two sides of the cylinder, and in the case of the other case actually you are pushing in this part. So, here for instance this is of course the inverse of this picture which is shown above, but nevertheless the concept is the same. So, you pull out this part and pull in this part, and therefore, you create an edge dislocation, and correspondingly the inner part also will move, the inner free part also will move, and which will create a step inside. In the case of screw dislocation, so you do not push and pull the way it has been done here, you actually slide one part, that means you pull the upper part and shear the lower part. So, it is some sort of a shearing motion. So, you apply a shear on the cylinder, one on the top and the bottom, to actually create a step now which is here, and corresponding there will be a step in this side also. So, I am using a cylinder, making a cut, and after the cut has been made, I slide one part of the free surface with respect to the other, and that is done by shearing forces. So, I can create things which we shall see have an analogy in crystals, but this is basically the continuum edge dislocation and the continuum screw dislocation. So, let me go over this slide, because this is perhaps often not discussed in detail in the crystallographic or crystal description of a dislocation. Herein we start with the perfect cylinder and perfect hollow cylinder. We make a cut here and separate out the two faces. So, I made a cut here, and therefore, now I got two free surfaces here. Afterwards, I do deformations to the cylinder, either by pushing in the top with respect and pulling the bottom to create a step along the length of the dislocation. So, I got a step here, or I can pull apart the two faces like this to create opening, and it is clearly seen in the two dimensional version of this figure, wherein you are pulling apart these two to create opening here, and these two would correspond to edge dislocations. If you want to make a screw dislocation, you actually use shear forces. And why is it called a screw dislocation? Because of the way the planes are. Suppose when you actually use a screwdriver to thread in a screw, you notice that when you go in the clockwise direction, you go one plane inside. So, that is what is happening here. You start from this point, and after the deformation is done, as you go around, you land up not in the same place, but deformed. There is a small displacement with the original. So, actually if you take individual slices of these planes, they will go spirally inward. So, this is what we might call a right-handed screw. We could of course create a left-handed screw also. There are other defects which you can create using this Volterra construction, and these are the disclinations, which are shown briefly here. We will not take up these in this case, but in the context of crystallographic defects, we had mentioned that these disclinations are associated with rotational symmetry. So, you can see that you can not only create dislocations, but you can also create these kinds of disclinations in using the Volterra cylinder. Now, we come to the most important part of this whole lectures, which is the dislocations in the crystallographic crystal, which is we shall see are two types, basically the edge dislocation and the screw dislocation, and which bear close resemblance to the edge and screw dislocation as described by Volterra. And we had mentioned that if you do a Volterra construction actually, which is now a continuum construction, we could actually get and try to those constructions to actually calculate the stress fields and strain fields. You can actually get the stress fields and strain fields, or even the crystallographic dislocation or the crystal dislocation. And of course, I told you that these calculations will be valid within a few Burgers vector, which is very close to the dislocation line. So, dislocations, suppose I typically look at a sample of aluminum. I take a material aluminum and I thin it down to less than about say about 1000 angstroms and look under a transmission electron microscope. So, typical sample of aluminum will consist of lot of dislocations, and you will notice that these dislocations are not straight, but actually they are curved. So, typically these dislocation lines will not be straight and they will be curved. So, these curved dislocation lines are nothing, have a mixed character, that means they are neither pure edge or nor pure screw. So, the ideal description of a screw and edge dislocations are nothing but extreme descriptions, and in most cases you will actually find only mixed dislocations. So, the norm is the mixed dislocation, the ideal ends, the edge and the screw, are the ways of understanding this mixed dislocation based on these extremes. Okay. So, but we will, in this course we will spend a lot of time on trying to understand the edge dislocation, which is the easier of the two to understand. The screw dislocation is slightly more difficult to understand, and we will have models to actually show how the displacement field of these dislocations are, how the planes are, but nevertheless the screw dislocation is more difficult to understand as compared to the edge dislocation. And once I understand these two extreme forms of dislocation, then we can make an attempt to understand this more complicated version of dislocation, which is the typical mixed dislocation. And why do I need to understand this mixed dislocation? Because typically you will find that any dislocation, any material will have a mixed character, and not only that, any curved dislocation will have this character changing from point to point. In other words, from position to position along the dislocation line, the character of the dislocation will change. That means how much of it, how much edge character it has got, how much a screw character has got, will keep on changing as you go from point to point along the curved dislocation line. There are special circumstances in which you will actually find a fixed character of a edge or a screw, or even a pure edge or a pure screw, and this of course can be found in pure tilt boundaries, wherein you will see that the pure tilt boundary, a small angle tilt boundary, can be visualized, which we will do of course later in this course, can be visualized as an array of edge dislocations. And a pure screw dislocation can be found in a twist boundary. And similarly, for instance, if you want a fixed character of for instance edge and screw, and this can be found for instance in an epitaxially grown GESI film on silicon substrate, wherein you will find 60-degree misfit dislocations, and these are straight dislocations, and the edge character is what is being described by this 60-degree, as we shall see later. So, you can have in special circumstances pure edge, pure screw, or what you might call a mixed dislocation of a particular character of edge character, but under normal circumstances you will find that the character is mixed, and not only mixed, it is varying from point to point along the dislocation line. So, we will take up the edge dislocation first, we will consider it in detail before we take up the screw dislocation, because many of the simple concepts can be understood using the edge dislocation, but the screw dislocation is slightly more difficult to understand.